Okay, our objective for this course and for this lesson right now is to understand about control hazards. We've come through structural hazards, we've come through data hazards. Data hazards were very interesting to see how we could work to solve them with forwarding and with hazard detection. Now we're going to look at the remaining category, which is control hazards. So if I could have your attention. All right, here we go. Control hazards, the third kind of hazard category that we must fix if we pipeline. This is not even a problem if you don't pipeline. If you go back to single cycle processors, you don't have these issues. But if you want performance, performance comes with a penalty, with a price. All right, control hazards are arising when the control flow of instructions changes and doesn't do PC plus 4. That's the classic, advance to the next sequential instruction. But we have change of flow instructions like branch, like jump. We have 4 branch instructions in the MIPS. You haven't yet seen all of them. We've seen this one, seen this one, seen this one. This is jump and link through a register instead of giving the direct address. It's like this one. It says the register has the value that I want to jump to. But it's with a link like this one, so it leaves a return address in the RA register of the place that you'll return to. So these are both call in order to return. These are go once, you're not coming back to this point. Okay. Our branch instructions, we're familiar with these two. And then there's a third category, which we haven't seen yet, called exceptions. And these are when something went wrong with the instruction, like there was a bad opcode or we had an arithmetic overflow, and we're not going to go to the next instruction. We're going to go to the operating system and ask for services to bail out from this mess. Okay, we fetched an instruction, we don't understand what it's supposed to be because the opcode isn't something that we can decode, or we had an overflow, et cetera, et cetera. There's lots of exceptions. We'll talk about those as soon as we finish the control hazards. So these 3 things cause us to jump to another place and not go to this. And the consequence of jumping to another place is that we didn't expect to do that. And the normal thing is fetch the next instruction, decode it, and start to operate it. But we don't want to do that. So pipelining is going to mean that we're going to have some issues with changing the flow and not doing the wrong thing. Some approaches are stall always, just wait until we can get the correct data. And of course, that is going to have a big impact on the CPI. You can always stall. You can fix any pipeline hazard by stalling. Just wait. Right? That fixes them all, but it fixes them at a penalty that we don't want to pay. What happens to the CPI if we stall? Does it go up or down? Up from what? Up from what? What's the CPI that we want to achieve? 1.0. Anything that stalls moves us up from that. This is our goal, is to have a fast clock cycle with a CPI of 1. In our pipeline. So anything that says stall says, CPI is going up. And of course, remember, time is equal to instruction count multiplied by CPI multiplied by clock cycle time. Make a small clock cycle time, make a small CPI, make a small instruction count, you're going to get a small time. We don't want this to go up because that's going to cause time to go up. Simple as that. Okay, another one is move the decision point about which instruction will go next as early in the pipeline as possible in order to reduce the number of stall cycles. All right? So this says don't do anything. This says change the hardware to shrink down the number of stalls. This one says reorder the code. We call it delayed decision. With compiler support, we might be able to put useful instructions in those stall places. So instead of doing no work, a lot of no work, or a little bit of no work, we do useful work. Okay, that's a possibility. We call it delayed decision. And then it's not because the decision is delayed, it's because there's some time in which we need to do something with the pipeline. Do nothing or do useful work. And then another possibility is predict which way the branch is going to go or the jump or whatever, and only stall on wrong predictions. In other words, if you predict correctly, you have no loss at all. You only have a loss of performance when you have wrong predictions. So this says stall always, this says stall sometimes, this says stall a little, this says if we can reorder the code, don't stall at all. But if we can't reorder the code enough, then we'll stall here as well. So all of them have the risks of stall, but this guarantees it. These try to do something. Okay, that's the idea. 4 possible solutions. We're going to look at this one, this one, and this one in order in the slides ahead. So we'll go into some depth about how these solutions would deal with the problem. Now, one good thing and one bad thing. At the bottom of the slide, you can read for yourself and see what that says. That's like the classic good news, bad news joke. The good news is, it doesn't happen nearly as often as data hazards. Bad news is, when it happens, we don't have a good solution like we had for data hazards. So if it happens, it's bad, but it's not going to happen nearly as frequently. Jumps are about 3% of the instructions. Branches about 17, 18, 20%. So we won't, about 20% total of the instructions fall into these categories. So 4 out of 5 instructions, we don't have this issue. 1 out of 5, we have this issue. So it's not nearly as frequent as it is for, remember loads and stores? What's their percentage? Loads and stores, about 45%. Arithmetic operations, about 33, 35%. Those are big percentage ones. If you have problems with those, you better have a good solution. Unfortunately, we do. We have forwarding as a very good solution. All right, now let's remember our data path hardware in order to do branches and jumps. If you remember, our red stuff is in control. We've put in a forwarding unit down here. We've got ALU control. We've got our main control. We're splitting out 3 control fields and carrying them forward 1, 2, 3 clock cycles. So all that is a control. We've got some branch hardware here. The ALU tells us if the subtraction result was equal to 0 or not. We catch it. We apply it in the memory stage with the branch instruction itself and determine if we're supposed to branch or not. And that's going to control this mux. In addition, the jump instruction is decoded, and that's going to control this mux. And these 2 muxes together form a 3-to-1. And they choose between 3 things. Next sequential address, branch target address, jump target address. And you can look at them real quick and figure out which one of these black arrows, 1, 2, 3, are the branch target, sequential, and jump target. Hopefully that's not hard to figure out. Okay? All right, so that's what we've got for hardware. Now we need to look at the problem and how we're going to fix it. Okay. So there we go. And notice we've got the forwarding muxes here now. They weren't part of our original design, but the forwarding unit is going to control these 2 muxes and decide, do we take this data or the one from this or the one from this. So we've got current data, forwarding 1 and forwarding 2 clock cycles ahead data. That's for the data stalls. Okay, now jumps incur 1 stall. Jumps are not decoded until the decode stage, right? So fetch it, decode it, and figure out that it's a jump. The problem is you've already fetched the next instruction. Or as you're decoding and figuring out it's a jump, you're also fetching the next instruction. So even though this says jump and go somewhere else, whatever this is got fetched. And we definitely don't want to execute it ever. So we've got to flush it. So whatever you fetched here, you've got to kill it. You've got to flush it. Bye-bye. Okay? And then what we want to do is go to the jump target address and fetch that and execute that. So what we really wanted to do was this, and then this. But in fact, we did this. We fetched this and have to kill it. And then so look what happened. Jumps essentially take 2 clock cycles. The jump instruction, the flushed, wrongly fetched instruction, and then finally we're in good shape for the one that follows. Everybody understand that? It's because in the decode phase, when I figure out it's a jump, it's too late to fetch the right instruction here. It's too late. Okay? So the decode phase is when I can figure out what the jump target address is. If you want to go back to the hardware and see how that works. In the decode phase, when I determine that it's a jump, this signal is going to say, okay, oh, it's a jump, so be sure that the PC is updated with the right one of these. Which one's the right one? Is it this one or is it this one? Bottom or top? Which one's the jump target address? Top, of course. Look, the top comes from shift left 2 of the 26-bit quantity coming out of the instruction, right? The 26-bit quantity, shift it left 2 to make it 28, and then merge it with the upper 4 bits of the incremented PC plus 4. So that's our pseudo direct jump target address. So that's the one I want to choose. Right, so this jump signal, when true, will choose the upper. When the jump signal is false, the lower will go through. So I'm able to figure it out in the decode stage, and that's when I know what the PC should be loaded correctly with the jump target address. Okay, great, but the problem is that's too late for this one. It's in time for this one. If I figure it out here, I know what to fetch here correctly. That's great, but not here. Okay? Everybody understand the problem? So jumps are going to cost us 1 extra jumps. The CPI of jumps is 2. It's very clear. 2 cycles to do a jump instruction. Not so good, actually. So we fix the jump hazard by waiting. We flush what we put in. Now, how do you flush? You fetched an instruction. How do you flush it? Just make it not do anything else. We fetched it. It's sitting in the register between IF and ID. Or it could be sitting there. How are we going to flush it? To make it do nothing the rest of the way. Make all control values to 0, or even make the whole instruction to be 0. Yeah, exactly right. All right, so let's go have a look at that. Since jumps only occur 3% of the time, it's not going to kill us that they're slow. All right? Remember, make the common case fast, but this is anything but the common case. This is the very uncommon case. So we don't like it that it takes 2 cycles, but it's not going to hurt us too much because they're infrequent. Now, there are 2 kinds of stalls that we need to distinguish between. All right, let's think about this. We already saw the kind of stall that we had for the load use hazards for data dependencies. Remember that kind of stall? You fetch something and decoded it, and now you want it to wait there and not move forward and just let the ones that are ahead of it in the pipeline finish, but to hold something partway through the pipeline, right? We did that before. That's inserting a NoOp between 2 instructions. So here we go. Fetch it and put it in the pipe. Fetch it and put it in the next one in the pipe. They're moving along, and what I want to do is right there put in a NoOp. That means this has to hold and this has to move forward so I can have a do nothing inserted. That's the kind we've already seen. Let's go through the, for the load use situation. You want to keep the earlier instructions in the pipeline where they are. You want to keep them from progressing down the pipeline. And so you need to be able to bounce them around or hold them right where they are, okay, with write control signals. Namely, don't write the new thing. If something's stored in a register and you don't write anything new on top of it, you've held the value. Or bounce it means don't push it forward. Just kind of juggle it right there. And so you insert the NoOp by zeroing the control bits in the pipeline, as Turkare said, at the appropriate stage. So things are moving along, and you're going to say, you hold right there, and what I'm going to do now is put zeros in, and that's going to cause the Boschluck that was left when we advanced. See, I'm not advancing this, and I'm holding it here. The Boschluck turns out to be a do-nothing by doing this. And so then you let the instructions which are ahead in the pipeline keep on going. They were earlier instructions, okay? And they just progress normally. So what you do is hold, let these advance, and right in the middle stick in the NoOp. Okay, that's inserting the NoOp. That's the kind that we had for the load use. Now we need a different kind right now for the jump. And that's the second kind here. That's going to be called a flush, okay? And the first kind is called a bubble, right, where you shish it into the middle of the pipeline a NoOp instruction. This kind is called a flush, okay, to get rid of an instruction that you fetched and live with the NoOp. Or squashing the instruction. Flush it or squash it. 2 different metaphors. Flush is CFON check, squash is, like that. And the idea here is you're going to replace the instruction with a NoOp. We're not inserting a NoOp and leaving all the instructions alone. We're actually saying to an instruction, too bad, you die, and you put a NoOp in place of it. You kill an instruction. We didn't kill anything here. We held some and let others move ahead, and when the Bosch loop that opened up, we put in a NoOp. This is not that. This is different. Okay, so what we're going to do here, like we're going to do for the J instruction, as you saw, is to zero out the control bits for the instruction that we're going to flush, or in this case, zero out all the bits in the pipeline register, the instruction fetch, instruction decode pipeline, right between fetching and decoding. If you zero them all out, then when you decode, they'll all be 0. In other words, this is even pre-decode. Okay, so let's see how that would work. We have a little mux here. And instead of letting what you fetched go in here, you choose to put a bunch of zeros in here. Well, obviously, if the instruction is all zeros, it's a NoOp. It's not going to write anything. It's not going to do anything. Let's think for just a minute about a NoOp instruction. If I had the following instruction, all zeros, let's analyze that instruction and figure out what it is. Okay. When I get 6 zeros in the beginning, what do I know? R-type. That means that I know a few other things. When I get 6 zeros in the beginning, then what instruction is it? Look here and find, is that too many? No, that's the right one. And then I look there and look at the function code. Well, the function code's not 32, function code's not 34, function code is 0. Would you mind opening your book and telling me what instruction is function code 0? Look up in your book. There's a nice table that shows, the green card in the beginning shows, but also in chapter 3 it shows. When you have an R-type and the function code is all zeros, what instruction have we got? SLL? Okay, shift left logical. Okay, shift left logical, as you know, takes a register value and shifts it to the left some number of bit positions, which is found in a different register, and puts the shifted result in the third register. So it's going to look like this: RD, RS, RT. This is going to tell me how much to shift. This is going to say what to shift. This is going to say where to put it. Well, can you look and see what I've got for RS, RT, and RD? Yeah, all zeros. Okay, plus I've got a shift amount. I'm sorry, the variable, that's for variable, excuse me. I've got a shift amount here, which is also zeros, so I think actually what we're saying here is shift it that much. So anyway, we're trying to take the 0 register and shift it and write it into the 0. All these are the 0 register, obviously. Okay, so what do you think is going to happen in this instruction? Absolutely nothing. So this is our definition. Shift left logical, 0, 0, 0 is equivalent to our NoOp instruction. No, we can't. We can't write into the 0 register. It isn't possible. It does nothing. It's exactly our NoOp. Does everybody understand? This is what you call a NoOp. All zeros translates to don't do anything. If you like what Ocon, try to do something which is impossible. This is the same thing as don't do anything. Okay? All right? So we got it? So there's our NoOp. So surely clearing the instruction to make it all zeros, which is what this mux will do, is going to result in this, which is our NoOp. Okay? So far, so good, right? All right, so now what we'll notice is the same jump signal coming out of here, which told this one choose the next PC, is telling this one flush it by putting in all zeros. So whatever it is that we fetched, we don't write it here. Okay? Right? So in the decode stage, when I found out it was jump, I'm telling the next instruction, which is being fetched, guess what? Haha, you're all zeros. So we fetched it for nothing. Boshunarashtik here, because we're not taking that, we're taking that. We killed it. We ised it. Right? What was the word here? We squashed it like a bug. Squash is a good word for bugs. Ooh, gross. All right. Okay? Everybody understand now? This is an important slide, though. We're doing this right now. We're squashing or flushing an instruction. Earlier we did this. I wanted that to be really clear that you understand there's two different things that happen in the pipeline. Okay, so there's the hardware. And everybody can see now that our jumps are going to take us 2 clock cycles. And I'd like to ask, what could we do to support instruction fetch stage jumps instead of instruction decode? See, we're doing the jump work here. And I'd like to ask you, is there any way that we could do the jump work here? Because if we did the jump work here, then there would be CPI of 1. We wouldn't have to squash anything. See, the problem is we're doing it here. We're figuring out where we go next here. We need to be figuring out where we go next here. Anybody have any ideas about how we could do that? We'd obviously have to modify the hardware, but we already have modified the hardware. Look what we've done. So we modified the hardware to get it to correctly operate with a CPI of 2. I'd like to ask you if you have any thoughts on how to modify the hardware to get it to correctly operate with a CPI of 1. Because that's what I really want, don't I? I don't want a CPI of 2. Even for a little 3% jump instruction, I want CPI of 1 if I possibly can get it. I don't want to stall. I don't want to lose any efficiency. A multiplexer with an enable. Okay, let's start. So what am I going to... First off, what's the output of this multiplexer going to go to? Actually, let's use the book symbol for multiplexers. Let's use the book symbol. Oh, I just want to mention something that I wrote there when you were doing the survey. Somebody said, can I have an extra survey form and fill it out for my friend also? And that made me think of a famous quote in American politics. There was a mayor, a very corrupt and crooked mayor of a city, and his party had a machine that was, kind of winning elections because they were doing a lot of unfair things. And he was quoted, and it's a famous American quote, before an election day, urging the citizens to vote early, vote often. Okay, now, do you get the joke there? Everybody has one vote on election day. But vote early, get out there early in the day and vote often. Several times during the day. Okay, that's the way that you can get elected if you tell your people vote early, vote often. Anyway, that goes down in the history of crooked politics. So no, you cannot fill out a survey form for your friend who's not here and vote twice. Sorry. All right. The suggestion was, let's have a mux. First question is, what are we going to do with it? Second question is, what's coming into it? And the third question is, who's controlling it? So let's explore this suggestion. Where did you make the suggestion? Yeah, what would you like to choose between, and where would you like to send it?
Between the address register of the jump and the jump instruction, I think I have to choose between three options.
Okay, and I think we want to send it into the program counter, don't we? That's the idea here, is get the right thing into here as fast as possible. So while we're in this, and this happens to be a jump instruction, we want to get the next thing, the jump target here in one clock cycle. If we fetch the jump, then we need to get the next, right, when the jump is here, the value of the target needs to be here. Everybody got this? If the jump instruction is here, then, Yanni, we fetched it, then you know what needs to be here? The address of the target. We can't figure that out here. We have to already know it. That means that while fetching the jump, we had to make some kind of decision about what the PC's next value should be. All right, so right now we have from, whatever you want to call it, branch and PC plus 4 and the slow jump stuff, but that didn't get the job done. That didn't get the job done. Right? That's all this stuff up here, 1, 2, 3 choices. We're just proposing something here that's smarter than that gets it done quicker. So what we really want to know is, what do I need to put here, and what am I controlling it with here to get the right value here on PC right? Okay? Normally speaking, it's equal to 1 almost all the time, isn't it? When the clock comes, then we write. Sorry. There we go. Okay. Oh, so we're expecting on the edge of the clock to load in something. That means this has to know what we're doing and this has to be ready. Let's go a little further. What would you like to have here?
26-bit address multiplied by 4 and 1 of 4.
Okay. Let's imagine that it's something like this. Jump target address. In fact, I want to make it like this. Jump target address table. Okay? So, for jump on line number 128, the pseudo direct JTA, which corresponds to that. We have another jump on line number 1028. So then the pseudo direct jump target address, that one. Does everybody agree that for every address of a jump instruction, there should be a, come back here, for every address of a jump instruction, there's an address I want to go to, which is this one. This J instruction and all the JRs and everything else, the JALs, they have a place they want to go to. Everybody agree? And wherever this says to go is not going to change over time. It's J, whatever, X or T or top of a loop or new procedure or integration library or whatever. So whatever its address is, that's fixed. So this address and this address actually have a Bire-Bire-Lishki. And I could put them into a table, couldn't I? I could have a jump target address table. And so now, if I address this thing correctly, out pops the place I want to jump to. So this is just like a little memory. Okay? And it could be loaded up by the compiler or the operating system at startup time, put them all in, the jump target addresses, and just what he said, take 26 bits, add 2 at the end, stick 4 in the beginning, and compute it, pre-compute it. These have to be pre-computed. And put them in here. And that'd be great for J and JAL. But the problem is JR and JALR don't work like that because they both need a register's value, and the register's value can change over time. That's the trouble with those. Yeah, and then the mux will choose. No, so now we have fast jumps, so we don't have that anymore. The mux will choose between branch and sequential versus jump, and the jumping will be done through the table instead of computing it the way that we did there. Everybody look and see what we've done here. Okay, let's go back to the hardware. Okay, here's the jump address, and we calculate it real time during execution. Here's the jump address. We pre-compute it and store it in the table. If it's a static jump address, that works just fine. If it's a dynamic jump address, that doesn't work just fine. Everybody see that? Okay, so for J and JAL, that would be a way to save a cycle. Pre-compute them, store them in a table. Okay, all right, I think it's time for a break. Let's do a break, and then please come back after break.